Hello. Today's lesson is about something called the product rule. Its product is what happens when you multiply. If you multiply two things together, you get a product. So here's 5 to the third power multiplied by 5 to the sixth power. And the issue, or the question is there a way that we could write this that's simpler, easier to work with? And it's based off the idea that 5 to the third power can be expressed as 5 times 5 times 5. And similarly then, 5 to the sixth power can be expressed as 5 times 5 times 5 times 5. And that just flew out there really quick. But this is 6 sets of 5, and there's 3 sets of 5. And if I was to just look at this whole string of multiplication, instead of looking at it as 5 cubed times 5 to the 6th, I could look at it as 5 times 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 5, which would be much easier if I could use exponents to express that, 5 to the 9th power. In other words, 5 to the third power multiplied by 5 to the sixth power is the same as taking 5 to the 9th power, because there are 3 factors of 5 and an additional 6 factors of 5 for a grand total of 9 factors of 5. Similarly, if I had 8 to the 4th times 8 to the 2nd, I'm really asking for 4 powers of 8 and 2 powers of 8. So in other words, there's a grand total of 6 factors there. So 8 to the 4th times 8 squared is the same as 8 to the 6th power, because there are 4 8s and an additional 2 8s being multiplied together for a grand total of 6 8s. Even if I don't know what the base is, as long as the bases are the same, they're both the unknown value x, I've got 4 of them and an additional 7 of them. And if I look at x to the 4th and x to the 7th and look at it all strung out, I would see that there are 11 x's all being multiplied together. So this is really x to the 11th power. So 4 x's and an additional 7 x's gives me a total of 11 x's all being multiplied, which is why I use exponents here. So it gets to the point, if you're looking at something ridiculous like this, some number to the 17th power times some number to the 12th power, this would be a really big pain to write out. In fact, there's 17 a's altogether and another 12 a's altogether, and the question is, can we find a way to get this expression simplified without having to list and then just count all of these up? I could count them right now. I could say there's, 1, 2, 3, 4, 5, 6, 7, 8. It looks like it was counted up, though. There's 17 of them there, and there's 12 of them here. If I multiply all these a's together, what should I get? The result should be a to the 29th power, because there's 17 factors of a and an additional 12 factors of a. All of them are being multiplied, so that's a multiplied by itself 29 times. So the thing about this kind of shortcut, the shortcut known as the product rule, is most students will memorize the part where you add the exponents, but we need to be a little bit more comprehensive in our understanding. The first thing we need to do is not just say add the exponents. We need to say under what conditions do we add the exponents. So the idea is if you have a number times itself this many times, multiplied by that same number, multiplied by itself 12 more times, then all we have to do is take all the times that a is being multiplied together and count up to get the total. This creates what is known as the product rule. So if you can look at a to the 12th times a to the 17th and see that there's a shortcut for multiplying so you don't have to string them all out, what if I had a to some unknown power and then a to some other unknown power? If I had expanded them out, I would have to write a times a times a m number of times, because there's going to be a total of m factors of a and an additional n factors of a. Now, I don't know how many to write out, but I know that there are m of these, an additional n of those. Therefore, a to the m times a to the n can be simplified as, well, what would it be? Hold on a second. I think that you figured it out, so I will tell you we're going to get I haven't figured it out, m plus n. So in other words, if you multiply two exponential expressions, the bases are the same, then we're actually tallying up the total number of times that base has to be multiplied by itself. So this is a formal definition for the product rule of exponents. Now, it's one thing to know what the product rule is. It's another thing altogether to know when you're supposed to use it. So we would look at this first, this whole series of different algebraic expressions and numerical expressions and ask, could I use the product rule to simplify this? This is 3 5 times, and then the 3 multiplied by itself 7 times. So is it a candidate for the power rule, product rule? Yes, it is. Here, though, I'm looking at this to be x times x, and I'm looking at adding x times x times x. Well, because of this multiplication, I can't really simplify or clean this up. This is x times x, which is one number. This is x times itself 3 times, which is a different number. And when I add them, well, I can't add them until I know what they are by order of operations. So I cannot use the product rule to simplify this. So a lot of times what students will do is they'll memorize the product rule, and then they'll get to a situation like this one and say that's equal to x to the 5th. That's demonstration of a complete lack of understanding and just basically just randomly throwing numbers together and hoping for the best. So don't do that. That's bad. All right, now I go over this one and say, can I use the product rule here? And so we have x times itself 3 times, x times itself 3 more times. Can I use the product rule? The answer is yes. What about here? Candidate for the product rule? I don't know how many times I'm multiplying 5. I also don't know how many other times I'm multiplying by 5. Could I use the product rule here? The answer is yes. See, the idea here, the conditions are, you need to have the bases to be the same, and you need to be multiplying them together. That's true here, the bases are the same, and they're multiplied together. And let's look at the next situation, where we have a times b, or a to the c, times b to the d. This would be a whole set of a's multiplied by a whole set of b's. Can I combine them? The answer is no, you cannot. Here, on the other hand, I have this a whole bunch of a's multiplied by another whole set of a's. So if I were to multiply these together, I would find I have an increasingly larger set of a's. So I could definitely use the product rule to simplify that expression. Here, there are 3 sets of 5 multiplied by 3 sets of 7. That does not qualify for use of the product rule because there's 3 sets of 5 and 3 sets of 7. I can't simplify that. Here, there's subtraction, so this is 25 and this is 625. I can't really do anything to the exponents to simplify this, so no product rule usage there. This one's interesting. 5 to the 3rd power, so I have 3 sets of 5, and then whatever x is, I have 2 more than that many more sets of 5, but I do know that all I'm doing is counting total sets of 5, so we'll have 3 sets of 5 plus this many sets of 5, so I could probably use the product rule there because the bases are the same, and I don't care how many exponents there are. And here again, I'm multiplying 2 exponential numbers where the bases are the same, so this is another candidate for using the product rule. So this is a quick summary of what you can and cannot use the product rule for. I suggest you pause the screen here and study this because these are all situations where the product rule is acceptable, and you'll start to say, all right, they all have multiplication and they all have the same bases. Here we either have addition, subtraction, multiplication of different bases. So either we have addition or subtraction, same bases, can't use the product rule. Or we have multiplication of 2 exponential numbers, but the bases are different. This is 5 and 7, or A and B. So when can you and when can't you use the product rule? Study this. Now the next issue is then, if we can use the product rule, how exactly will we use the product rule? In the first case, 3 to the 5 times 3 to the 7 should be rudimentary. That's 3 to the 5 plus 7, which is 3 to the 12. Second one, there's 3 x's times 3 more x's, so that's a total of 3, or x to the 6th power. Here we have 5 to the x power and 5 to the y. I don't know how many x's there are, how many y's there are, but I do know how many total 5's will be multiplied together. It's x plus y 5's. So if this is 3 and 7, then this would be 10. 3 plus 7 is 10, 5 to the 10th power. A plus b and minus b. I don't know much about those, but I do know I can add those together, and then a plus a is 2a, and b minus b is 0. So the simplification of this product is really a to the, or x to the 2a power. And then use the same thing, add the unknown exponents here, add the unknown exponents here, and then collect like terms. 3 plus 2 is 5. So instead of taking 5 cubed times 5 to the x plus 2, I could just take 5 to the 5 plus x power. and get the same exact results as I did up here. One last little interesting follow-up. When we studied exponential growth functions, we made an observation that shifting a graph horizontally has the same effect as stretching a graph vertically. And I want to see if maybe this product rule can help us understand this. First of all, reminder, 3 to the x plus 2 is exactly like 3 to the x, only it has been shifted to the left 2 units. So the red graph represents 3 to the x, and the blue graph is shifted that red graph over 2 units, and so that's what you see here. Notice here it shows all of the x values are 2 over to the left because of our transformations. Now in this case we have 9 times 3 to the x, and I have the red graph, which is just regular old 3 to the x, and we can observe that however far from the x-axis our red graph is, I can go 1, 2, 3, 4, 5, 6, 7, 8, 9 times the length, and I'll be at the blue. Here's a little teensy original length. 9 times that, though, takes me up to here. Even here, there's a little bit of a length. 9 times that length is going to be way up off the graph. So this, you can see the 9 causes a vertical stretch of y equals 3 to the x. Put the graphs side by side, we see a vertical stretch by a factor of 9 is the same as a shift to the left 2. How is it possible that we could stretch 9 and get the same result as if we shifted left 2? The key lies in the product rule. Let's start with y equals 9 times 3 to the x. I can really write that as 3 squared times 3 to the x. Now I actually have two of the bases are the same. This is 3 to some power times 3 to some other power, which means even if I rearrange them, I can now use the product rule and say this is 3 to the x plus 2 power. So now we see why we get the same graph. The vertical stretch can be morphed into a horizontal shift and get the exact same values. So math magic for y'all. So our conclusion here is the product rule can actually be used 2 different ways, but the product rule can be used actually multiple different ways. But if you ever had a function like f of x equals 4 times x, or 4 to the x plus 3 power, you could write it as x to the 4th times, or sorry, 4 to the x times 4 to the 3rd, and 4 to the 3rd is 64. So this vertical stretch of 64 is the same as a shift to the left of 3 for a base 4 exponential function. All right, later.